Yeah, it's clearly visible.
Okay.
Okay, so we will go for. Okay, so we are going to have the second speaker, Professor Nishad-Kothari from IIT Madras. So he did his PhD from University of Waterloo, Canada. Then he held several postdoc positions in University of Campinas, Brazil, then University of Vienna, and also University of Waterloo. Yeah, his research area is structural graph theory with a focus on matching theory and combinatorial optimization. So over to you, Nisar.
Sure. Okay. Am I audible?
Yeah.
Okay. Thanks. Hi, everyone. Thank you, Dina, for the invitation and to the other organizers. Yeah, so it's really nice to be here. Well, we are not in the same place, but well, that's okay. We are in 2025. So yeah, anyways. So yeah, my research is in structural graph theory. In particular, I work only on perfect matchings. And of course, if somebody says that, you may be, oh, what is there to do in perfect matchings? So let me just let me tell you that there is actually a huge number of solved as well as open problems. And over the period of these 2 hours, I will try to tell you about some of the problems. And my main focus is actually going to be on theory, right? So one of the points I want to convey is that problem solving is great, but let us not ignore theory, because theory is what really helps us in solving lots of problems using the same framework, right? And getting ad hoc solutions to problems is not very satisfying. So anyway, so that's going to be one of the themes of my talk. Right. So perfect matchings. And let me just start by defining a perfect matching in case anybody is not familiar or doesn't recall. So here is an example of a graph. And here is a perfect matching of the graph. The blue colored edges, if you look at any vertex, if you look around any vertex, you will see exactly one blue colored edge incident at that vertex. So if V is any vertex, partial of V is the set of edges incident at V. And among these edges, you will see exactly one blue colored edge. Such a set of edges is called a perfect matching of the graph, right? So there is a lot of work on matchings and perfect matchings. And of course, many of you may know that testing whether a graph is a perfect matching or not is a polytime solvable problem. And there is a nice theorem that characterizes all graphs that have a perfect matching. Right? So I'll actually state these things in due course of time. Right? So this is one perfect matching of the graph. Can anybody tell me how many perfect matchings in this graph? In this particular graph? I'll give you a hint. Look at this cut. What is a cut? A cut is a set of edges that goes from one part of the vertex set to another part of the vertex set. So I'll partition the vertex set into two sets, X and X complement. And now a cut is all edges that have one end in X and the other end is an X complement, right? So if you look at this cut, then you can count the number of perfect matchings in this graph quite easily. For example, if you take any perfect matching of this graph, observe that M intersection partial X, where partial X is any cut and M is a perfect matching, observe that this is always congruent to X mod 2. This is often called the parity lemma. There are lots of parity lemmas. This is one of them. So that means the number of edges in this cut in your perfect matching has to be an odd number. The cut has only 3 edges. So the intersection of m and partial x is either 1 or 3 for each perfect matching. And if you take all 3 edges, you have a perfect matching. That's one perfect matching. And if you take any one of the 3 edges, like the blue perfect matching here, you will get a particular perfect matching. So you have 3 perfect matchings for which this intersection is 1. There are 3 such perfect matchings. And you have 1 perfect matching for which the intersection is 3. And therefore, the total number of perfect matchings is 3 plus 1 equal to 4. Yeah. Okay. So that's our small example. Any questions, concerns? Is everything clear so far? Okay. So observe that this graph is a 2 connected 3 regular graph. Right? 3 regular graphs are also known as cubic graphs. And what we observed is that this graph has not only 1 perfect matching, it has 4 perfect matchings. And if you look closely, there is a perfect matching containing every edge. There is a perfect matching containing every edge. This was already known to Schoenberger. Schoenberger in 1934 proved that every 2 connected cubic graph has the property that each edge belongs to some perfect matching. Let me just write it like this. In any 2 connected cubic graph, each edge belongs to some perfect matching. Okay? We will actually see a proof of this using Tutt's theorem soon. I'll tell you what Tutt's theorem is, and then we will use it to prove this. Are there any questions or concerns at this point? Yeah, feel free to interrupt me at any point, right? Okay. In fact, a weaker version was known to Peterson, the famous Peterson of the Peterson graph, in 1891. Peterson already knew a weaker statement, which is that every 2 connected cubic graph has a perfect matching. I will abbreviate perfect matching to PM. Okay. So this was already known to Peterson in 1891, and this has connections with the 4-color theorem, which was, of course, back then the 4-color conjecture. Right? And Bill Tutt stumbled upon the proof of this theorem as a teenager. And this proof was quite non-trivial. In fact, I've never read this proof, nor do I intend to, because now there are much shorter proofs. Right? So Bill Tutt had actually stumbled upon this proof in his younger years, and it kind of stuck in his mind that this is a really complex proof. It would be nice to have a shorter proof. And that is what he did many years later by proving Tutt's perfect matching theorem. And then this is just a corollary. In fact, not only this, Schoenberger's result is also a corollary. Okay. But before we go into that, let me point out one thing here. This property, each edge belongs to some perfect matching. This may seem like a very strong property if you are seeing it for the first time. However, let me convince you that if your only interest in life is perfect matchings, which is the case for me, then this is actually a reasonable property. You can actually restrict yourself to graphs that have this property. Okay, so I will try to convince you in the next page why we may restrict ourselves to graphs that have this property. So what is a matching covered graph? Matching covered graph. A matching covered graph has two properties. One, it is a connected graph. And two, the more interesting property is that each edge belongs to some perfect matching. Okay. So as I said, this sounds like a very strong property, but let me convince you why you shouldn't care about other graphs if your interest is perfect matchings. Supposing you want to count the number of perfect matchings in a graph. Many of you may know that this is actually a very difficult problem. This is sharp P complete. This was shown by Valiant, 1979. It is a sharp P complete problem, which basically means that, let me not go into sharp P, which essentially means that unless P equals NP, no polytime algorithm. Okay. But let's suppose you want to count the number of perfect matchings in a graph, right? So let's consider a particular graph. Here is a particular graph. Let me label the vertices 0, 1, 2, 3, 4, 5, 6, and 7. Okay. I hope everybody can see that this graph has at least one perfect matching. And probably you can already see more number of perfect matchings. I have a question. There is one edge I can remove, and the number of perfect matchings will not change. Can anybody tell me what is that edge? There is an edge here. I'm looking at the chat also, by the way. So if you want to reply on the chat, that is also fine. There is an edge here that can be removed so that the number of perfect matchings does not change. 1, 6, exactly. 1, 6 is an edge that you can remove and it will not change the number of perfect matchings, right? And the reason is because this edge does not belong to any perfect matching. Therefore, you can throw it away and it will not change the number of perfect matching. So let's throw it away. Let us throw this edge away. Oh, sorry. Yeah, okay. Anyways, I will erase it and draw things again if I need to. Yeah. So this is the graph without that edge. That was this edge, and we just erased it. Now, is there any edge? Is there any edge in this graph that we can remove so that the number of perfect matchings will not change? Can we still remove any other edge and not change the number of perfect matchings? It's a trick question. Okay, since nobody is replying, I'm assuming you are all saying no. If you remove any edge from this graph, you will change the number of perfect matchings. Thank you. Yeah, that's right. And the reason is because in this graph, every edge belongs to some perfect matching. In particular, this graph is not even connected. So what you can do is you can look at the connected components. This is one component. This is another component. And these graphs have the property that we have written here, the two properties. They are connected graphs and every edge belongs to some perfect matching. Therefore, in order to count the number of perfect matchings in the original graph, we can just count the number of perfect matchings in these connected components and multiply them. That is the number of perfect matchings in the original graph, right? So hopefully you all are convinced that to count the number of perfect matchings, you can assume that these two properties hold. And observe that checking whether an edge is in a perfect matching is clearly polytime. I hope you all can see that. That checking whether an edge belongs to a perfect matching is a polytime. So you can just identify all such edges, throw them away, and work with the connected components of the resultant graph. Okay, so that is what a matching covered graph is. This is just one example. I could give you one more example. Consider the perfect matching polytope of a graph. What is a perfect matching polytope?
So you are checking, given a perfect matching, the edge belongs to that checking.
No. Given an edge, does it belong to any perfect matching? Given any edge, does it belong to any perfect matching of the graph?
So how are you checking?
You delete the two ends of that edge and check whether the resulting graph is a perfect matching. And that is polytime. Yeah. Okay, good. Thank you. So that is why you can check it in polytime, right? And you can basically remove all such edges and then just look at the connected components. Those are matching covered graphs. So I'll give you one quick another example related to the perfect matching polytope. So what is a perfect matching polytope? You think of each perfect matching as a vector. For example, if the perfect matching is a set of green edges, you put a 1 on all these edges in all the entries corresponding to these edges, and you put a 0 everywhere else. So each perfect matching can be viewed as a 0, 1 vector in Re, where E is the number of edges. Right? And now because you can view it as a vector, you can take the convex hull of all such vectors. That is a very well studied object in combinatorial optimization and polyhedral combinatorics. So you can ask a lot of questions related to the perfect matching polytope. Many such questions were answered by Jack Edmonds in 1965. And there is a lot of work on the perfect matching polytope and various other polytopes arising from graph theoretical combinatorial concepts. But if you are interested in the perfect matching polytope, I claim that again, you can forget about the edges that are not in any perfect matching. Because in every vector, those entries will be 0. They are not contributing anything interesting to the problem, right? So you can just throw away all the edges that are not in a perfect matching, and then you can understand the perfect matching polytope of the resulting graph. And as usual, you can restrict yourself to the connected components. Because if you understand the connected components, then it is easy to understand the entire graph. Okay. So any problem that arises from the perfect matching polytope, I will not go into specific problems in the interest of time here, but you can watch some of my YouTube videos where I talk about problems related to the perfect matching polytope, right? So for any problem related to this object, you can again restrict yourself to matching covered graphs. And if you solve the problem for matching covered graphs, you can solve it for all graphs in the world. Okay. Any questions, concerns? Okay. If not, let us restate the theorem from the previous page. On the previous page, we wrote down, in any two connected cubic graph, each edge belongs to some perfect matching. Now I can rewrite this saying that every two connected cubic graph is matching covered. Okay. So let me rewrite this part. Every two connected cubic graph is matching covered. And I shall abbreviate this to MC from now on. Okay. All right. And there is a lot of theory on matching covered graphs. Let me just convince you by showing you a textbook that was published in 2024. This book is called Perfect Matchings, a Theory of Matching Covered Graphs. Right? It's around some 550 pages of a book on just matching covered graphs by Lucchesi and Murthy. Murthy from Bondi and Murthy, and Claudio Lucchesi from Brazil. Right. So there is a lot of literature on matching covered graphs, and pretty much everything I'm talking about is contained in this book. But of course, the book has a lot more than what I can cover in 2 hours. Right? So I strongly recommend buying this book if you're interested in working on problems related to perfect matchings, or if you're interested in just learning about it. Yeah. Okay. So the next goal for this talk is to prove this theorem. I would like to prove this theorem using the famous theorem of Tutt that characterizes all graphs that have a perfect matching. Okay. So we will first see that theorem of Tutt, which is covered in my video lectures that I had shared with you. So I will not be proving that. I will just remind you what that theorem is. And once we have that theorem, we will apply it to prove this one. Okay? Okay. So the big open question. So I'll change the pen. The big open question back in the day was characterize graphs that have a perfect matching. Okay, let me phrase this as a decision problem and also relate it to some complexity classes NP, co-NP, and P. Okay, so here is a decision problem. Decide whether a graph G has a perfect matching or not. Right? So I hope you are all familiar with decision problems. You either say yes, there is a perfect matching, or you say no, there is no perfect matching. Right? And in each case, you want to also give a certificate to convince the other person that the answer is correct. Right? And when there is a certificate that can be easily verified here means in polynomial time or deterministic Turing machine. If you don't know those things, don't worry about it. We will go with intuitive understanding. Right? So if you can, for example, let's do an example. Supposing I want to convince someone that a given graph is a perfect matching, what would I show to them? If I want to convince you, or you want to convince your friend that a given graph is a perfect matching, what would you show to them? Is it easy to convince somebody that a given graph is a perfect matching? Give the witness, give the perfect matching. Exactly, right? So you just show the perfect matching and that's it. So therefore, clearly, this problem belongs to NP. It belongs to NP, and the certificate is any perfect matching is a certificate. Yeah. We are not talking about how to find a perfect matching. Okay, that's about P. That is not about NP or co-NP. Okay. So if you want to convince somebody that a graph is a perfect matching, you just show them a perfect matching. Done. Now consider the other situation. You want to convince somebody that a given graph does not have a perfect matching. How would you convince somebody that a given graph does not have a perfect matching? And let's do one example. So remember Schoenberger's theorem. It says every two connected cubic graph each edge belongs to some perfect matching. Here is a cubic graph. In which there is no perfect matching. You might say, oh, there are parallel edges. Yes, we allow parallel edges. I will also show you an example without parallel edges. Right? So in matching theory, we allow parallel edges. We don't allow loops because loops are useless. They don't participate in perfect matchings. But in general, in matching theory, we allow parallel or also known as multiple edges. Okay. So here is a cubic graph. Clearly, it is not two connected. But more importantly, it also does not have a perfect matching. Can anybody tell me why this graph does not have a perfect matching? Can you see a certificate for the same? I have labeled the vertices. Can you see a certificate for this particular example or an argument that will convince anybody that this graph has no perfect matching?
Because odd number of vertices?
No, there is even number of vertices, 0 to 9.
Oh, 0 you have started. Okay.
Yes, I've started with 0. Yes, yes. Thank you.
So there are odd number, like the components, each component has odd number of vertices. If like component means these triangles, if you look.
You are looking at components of a certain subgraph, it seems.
Yes, when I remove 3.
Can you repeat that?
When I removed vertex.
Remove 3, exactly. Great, great. Consider the graph G minus 3, where G is this graph and minus 3 means delete the vertex 3. Okay, consider this graph. This graph, after you delete this vertex, has 3 components. 1 component, 2, and 3 components. All these components have odd number of vertices. So therefore, they cannot have a perfect matching within themselves. Right? So to have a perfect matching in this graph, you have to match a vertex from this triangle outside. You have to match a vertex from this triangle outside. And you have to match a vertex of this triangle outside. Well, that means you have to take these 3 edges, but then it is not a perfect matching. Right? So that is an argument as to why this graph does not have a perfect matching. Yeah. But now let us generalize this. So if in any graph, if you have a graph G and you delete a set of vertices, let's say you delete some set of vertices, 1, 2, 3, 4, and you may get some components. Supposing the number of odd components, odd meaning they have odd number of vertices. Supposing the number of odd components after deleting these 4 vertices exceeds 4, like I have drawn here, I have drawn 5 components. I will draw even components as boxes and odd components as circles. Okay, even components won't play a role, don't worry about them. Supposing I delete these 4 vertices in my graph and I get 5 odd components, then it is easy to see that this graph has no perfect matching because each odd component, it has to match at least 1 vertex outside. So when outside means it has to go to the set S because they are components of G minus S. So this odd component has to match one of its vertices to S. Same for this odd component and so on. But there are 5 components and only 4 vertices. Right? That's a problem. So you can't do that. So therefore, if you find a set like this, S of the vertex set, then you know that your graph does not have a perfect matching. And this is what Tutt proved. Whenever the graph does not have a perfect matching, there will be a set S for which the number of odd components in G minus S is strictly greater than S. Okay, let's write down this theorem. So this is Tutt from 1947. A graph G does not have a perfect matching if and only if there exists a set of vertices such that the number of components that have odd number of vertices in G minus S is strictly greater than the cardinality of S. This is what Tutt proved in 1947. Right? This is a seminal result in graph theory because people knew about bipartite graphs. Hall's theorem was known for a long time, which tells you when a bipartite graph does not have a perfect matching. But people did not know how to say whether a non-bipartite graph does not have a perfect matching. And this theorem, of course, applies to all graphs. Hall's theorem is just a special case of Tutt's theorem. I mean, it needs a little bit of work to derive the exact statement of Hall's theorem from Tutt's theorem, but it is not difficult. It's an easy exercise, right? So this is the theorem Tutt proved. And now let us go back to our decision problem. Now I want to ask you, does the problem belong to co-NP? NP means yes instances admit an easy certificate, easily verifiable certificate. Co-NP means no instances admit an easily verifiable certificate. So now using Tutt's theorem, what can you say about this decision problem? Yes, what does yes mean? Witness is the bad set. Yes, sure. Okay. So Tutt's theorem basically puts the problem in co-NP, right? And the witness is the bad set. Bad set meaning a set that satisfies this condition. Yes. Does not have a perfect matching if and only if there is a set for which the number of odd components in G minus S is strictly greater than the cardinality of S. Such a set is called a Tutt set. What is a Tutt set? This. Such S is called Tutt set. Okay? Good. So Tutt proved this, and then Tutt's theorem immediately proves that every two connected cubic graph has a perfect matching. This is the weaker statement. This was proved by Peterson in 1891. Every two connected cubic graph has a perfect matching. So let me quickly convince you why this statement is true using Tutt's theorem. Okay? And you can see that two connected is necessary because in this example, it's a cubic graph. It is not two connected. There is a cut vertex. In particular, there are cut edges, which is not a coincidence because for cubic graphs, vertex connectivity is equal to edge connectivity. Okay, this is a well-known fact. It's not difficult to prove. So you have cut vertices or you have a cut vertex and you also have cut edges, right? So you need two connectivity for a cubic graph to have a perfect matching. And if you are not happy with multiple edges, let us get rid of the multiple edges, subdivide these edges, and now you have a simple example, a graph without multiple edges. Right? This is a cubic graph where there is no perfect matching. Any questions, concerns before we proceed to prove Peterson's theorem? Okay, if there are no questions or concerns, I will erase this example and we will prove Peterson's theorem using Tutt's theorem. Okay. Let's just remind ourselves what we are trying to prove. So we will take a two connected cubic graph. We'll take a two connected cubic graph. And our goal is to show that the goal is to prove that G has a perfect matching. Okay, So here is how I want you to think about this. This is a particular problem we are trying to solve. Every two connected cubic graph has a perfect matching. We're trying to prove this, right? And here is the theory. Tut's theorem is a very powerful statement that is not about two connected graphs. It is about all graphs in the world, right? This is the theoretical tool that we are going to use to attack this problem, and we are going to just finish it off in few lines. Okay? Questions or concerns before we start? You can also type questions or concerns in the chat. I will be looking at it. Okay, so if not, let us begin. Let us take a set of vertices. So let S be any set of vertices. And I would like to convince you that the number of odd components has to be less than equal to the cardinality of the set S. Okay? So let's say we have 4 vertices, where 4 is any number. It doesn't matter. Okay? Supposing I am deleting 4 vertices from my graph. And let's suppose, for the sake of contradiction, we get 5 or more odd components. Or forget it. Let's not even worry about contradiction. Let's just look at an odd component. Supposing this is an odd component of the graph G minus S. Let us just look at an odd component, because if there are no odd components, we don't need to do anything, right? So supposing there is an odd component, let's try to understand what will happen. So let's say this component is J, and I want to ask you how many edges are in this cut. What is this cut? This is the edges leading from J to outside J. The edges that have one end in J and the other end is outside J. Okay? So what can you say about the number of edges in this cut, given that the graph is two connected? How many edges should leave from J and go to outside J, given that the graph is two connected? At least two. At least two edges, right? This quantity is at least 2. Now I want to ask you a question. Can you use the fact that this is a cubic graph? Cubic means every vertex has degree 3. Can you use this fact to make a stronger lower bound? At least 2 is correct because it's a 2 connected graph. Now I want to use the fact that this is a 3 regular graph and I want to strengthen this further. And remember that J has odd number of vertices. You have an odd number of vertices. Every vertex in the graph has degree 3. Can you make this bound stronger? I'll give you a hint. Use the handshaking lemma. What can you say by using the handshaking lemma? Okay, let me give you a hint. The hint is there is some relation between this and this. These two quantities. The number of edges in this cut and the number of vertices in the odd component. There is some relation between these two using the handshaking lemma. Can anybody see what that is? Can you have exactly 2 edges leaving from an odd component in a 3 regular graph? odd number of edges must exist. Exactly. The number of edges in this has to be at odd number because the parity of these two, this is another parity lemma. Matching theory has lots of parity lemmas. Another parity lemma. These two have the same parity. This is an easy argument using the handshaking lemma. Okay? Because there is an odd number of vertices, the number of edges leaving must be an odd number. Therefore, it cannot be exactly 2, it must be exactly 3. It must be at least 3, sorry. It must be at least 3. So you have at least 3 edges leaving from here. Now can you finish the argument yourself? Let's, right, so for every odd component, the number of edges leaving from that component is at least 3. Now, I claim that we are done. It's just simple counting. I want to conclude that the number of odd components in G minus S is less than equal to the cardinality of S. This is what I want to claim. If we claim this, if we prove this, then by Tut's theorem, we are done. The graph has a perfect matching. Because we took an arbitrary set of vertices. Right? So let's just finish this point. We're basically done. Let me actually just convince you through a small example, and I will give the writing of the formal proof as an exercise. Supposing we had 5 components. I have 4 vertices, and supposing I have 5 components. Let's just do some counting. For every odd component, I'm referring to odd components. For every odd component, there will be at least 3 edges leaving. At least 3 leaving. So in this case, I will get at least 15 edges. These 15 edges have to go into this set. But the set has only 4 vertices. Therefore, only 12 edges can leave from the set. So I have 12 edges leaving from the set, but I want 15 edges to enter the set. So that's not possible. Right? There can be at most 12. This is at most 12. The number of edges leaving is at most 12 if you count from this side. And if you count from this side, the number of edges is at least 15. At most 12 cannot be at least 15. So we are done. Questions, concerns? Okay. So if everybody is convinced, we have proved Peterson's theorem using Tut's theorem. Every 2 connected cubic graph has a perfect matching because every set of vertices satisfies this inequality. And that is the same as saying that the graph is a perfect matching. Okay. So now the question is, how do you prove Schoenberger's theorem? We proved that every such graph has a perfect matching. Now we want to prove the stronger statement. Every edge belongs to some perfect matching. Okay. Every edge belongs to some perfect matching. Okay. But before we prove that, let me use one terminology. I will say a graph is perfectly matchable if it has a perfect matching. Okay. So let me just write here a graph G. Tut's theorem says that a graph G is not perfectly matchable. If and only if this happens, right? So not perfectly matchable means it does not have a perfect matching. Okay. So I will use this terminology. It will just make things a bit shorter. Okay. Are there any questions or concerns? If not, the next goal is to prove Schoenberger's theorem. What does it say? We have a 2 connected cubic graph. G is a 2 connected cubic graph. We have already proved Peterson's theorem. So we know that G is perfectly matchable. It has a perfect matching. And our goal is to prove that each edge of the graph belongs to some perfect matching. Okay? Is the next goal clear? We know that the graph is a perfect matching. Now we are trying to prove the stronger property that every edge belongs to some perfect matching of the graph. Okay. We will come back to this page in a few minutes. Before that, we will first try to understand the more general question. When does an edge belong to some perfect matching? Okay? Because we want to prove that every edge belongs to some perfect matching. So let us go back to theory and then we will come back to this problem. Okay? So now I'm going to assume that G is a perfectly matchable graph. And what I want to understand is when does an edge belong to some perfect matching? When does a given edge UV belong to some perfect matching? Right? This is what we want to understand. And if and only if statement. But let me make this actually more general. So we observed earlier, I think there was a question by Dina maybe, that how do we check whether an edge is in a perfect matching, right? And the answer is you check whether G minus U minus V has a perfect matching, right? So we know that UV belongs to a perfect matching if and only if G minus U minus V has a perfect matching. Yeah, everybody sees this? Okay. So instead of answering this question, let us look at this for any two arbitrary vertices. Let us consider two arbitrary vertices, U and V, and let us try to understand when does G minus U minus V have a perfect matching. If we answer this question, we should be able to answer it for adjacent vertices also. Okay. So I'm going to change the question. Given U and V, distinct vertices, U not equal to V, when does, or let me ask, when is G minus U minus V perfectly matchable? Is the question clear? Does everybody agree? If we answer this question, we should be able to answer our original question. When does an edge belong to a perfect matching? Okay. So now we'll try to answer this question. Okay. But we already know from Tutt's theorem, when is a graph not perfectly matchable, or when is a graph perfectly matchable? So we can use Tutt's theorem to understand the answer to this question. Right? And we know that the original graph is perfectly matchable. Okay, so from now on, I will assume that my graphs are perfectly matchable because I can use Tutt's theorem and I can throw away the remaining graphs. So now I want to assume the graph is perfectly matchable and understand the answer to this question. So let's try to understand this. Supposing this graph does not have a perfect matching. Supposing after deleting two vertices, my graph does not have a perfect matching. That means that in G minus U minus V, there is a Tutt set. There exists a Tutt set. Suppose G minus U minus V is not perfectly matchable. Then it implies that in this graph, there exists a touch set. So let's draw a touch set. Supposing I delete 4 vertices and I get more than 4 odd components. Yeah. I have deleted 4 vertices in G minus U minus V and I have 5 or more odd components. Let's try to understand this situation. Can I have exactly 5 odd components in this situation? I delete 4 vertices and I have exactly 5 odd components. Can this happen? I'll give you a hint. Parity. Can we have exactly 5 odd components in G minus U minus V minus the set T? And remember, the original graph is perfectly matchable. So it has an even number of vertices. So can we have the situation? Just add the number of vertices. 5 times an odd number. Well, 5 odd numbers added. That is an odd number. Number of vertices will be odd. Exactly. There are 5 odd components. So you get odd number of vertices plus 4 vertices. Odd number plus 4 is odd. So therefore, you can't have 5 odd components. You must have at least 6 odd components. You must have at least 6 odd components. It could be 6, it could be 8, it could be 10. Yeah. But remember, the original graph has a perfect matching. The original graph has a perfect matching. So can we have 8 odd components? We know we have at least 6. Can I have 2 more? Can I have 6 plus 2? Now think about the original graph. The original graph has a perfect matching. Can you have 8 odd components? If you have 8 odd components, go back to the original graph. Put U and V back here and add it to the set T. You get another set T star. Now observe that in original graph, I delete 6 vertices, I get 8 odd components. So the original graph has no perfect matching. But that is a contradiction, right? Therefore, I cannot have 8 odd components. I must have had exactly 6 odd components. Otherwise, we get a touch set in the original graph, and then the original graph does not have a perfect matching. Contradiction to our hypothesis, right? So therefore, there are exactly 6 odd components in G minus U minus V minus T. And when I put back the 2 vertices, I am deleting 6 vertices and I'm getting 6 odd components. Okay. So the point is, what we just proved is number of odd components in G minus U minus V minus the set T is exactly the number of vertices in T plus 2. And now, if I consider this as T star, if I consider U plus V plus T as T star, then this is exactly cardinality of T star. So in the original graph, we have this situation. We are deleting a set of vertices and we are getting exactly that many odd components. Okay? This is the situation in which the graph G minus U minus V is not perfectly matchable. And you can also prove the converse. The converse is actually quite easy. So here is the theorem. Here is the corollary we just proved. This is the corollary of Tut's theorem. G is a perfectly matchable graph. U and V are 2 vertices that are distinct. U is not equal to V. Then G minus U minus V is not perfectly matchable if and only if it is not perfectly matchable if and only if there exists a set T in the vertices of G such that U and V are in this set. U and V are in this set, and the number of odd components of G minus T has the same cardinality as T. Let me change the name to B. This T is becoming confusing. I'll call it B, and you will see why I'm calling it B. Okay, so this B is T star over here in my proof. Okay, so you are deleting some number of vertices from the graph, and you are getting as many odd components as the number of vertices you deleted. Okay, and the two vertices U and V are in this set. In this case, you can say that the graph G minus U minus V is not perfectly matchable, and it is if and only if. Are there any questions or concerns? There is one concern. There is a lot of words over here. Let us try to reduce the number of words by introducing a definition that is actually very important in matching theory. So, Tutt's theorem tells you that in a perfectly matchable graph, if you delete any set of vertices, the number of odd components will be less than equal to the vertices you deleted. The sets for which equality holds, those sets for which equality holds, they actually play a very important role in matching theory, which is not surprising because Tutt's theorem gives you this inequality for every subset of the vertices. And you can see that it naturally comes up in our proof here. So the sets for which equality holds, they are called barriers. So what is a barrier? A barrier is a subset of the vertex set such that the number of odd components after deleting this vertices is exactly equal to the cardinality of the vertices. This is what is called a barrier. Okay, and what we just proved here is that G minus U minus V is not perfectly matchable if and only if there is a barrier that contains U and V in the graph G. Okay, so I am going to erase this and I am going to write a simpler statement here. If and only if G has a barrier containing U and V. Any questions, concerns? So we have answered this question. Given a perfectly matchable graph, you consider two distinct vertices, U and V. The graph G minus U minus V is not perfectly matchable if and only if the graph G has a barrier containing U and V, which means that there is a set of vertices that contains U and V, so that the number of odd components in G minus B is exactly equal to the cardinality of B. Such a set is called a barrier. Yeah. And now, using this corollary of Tutt's theorem, we will go back to the previous page and we will prove Schoenberger's theorem. Yeah. Okay. I want to ask Dina, Should we take a break here or should I continue? I'm okay with either.
We can take a 5-minute break if you want.
5 minutes break? Yeah. Okay, sure. So we
Okay.
will resume in 5 minutes.
Yeah.
In the meantime, if anybody has questions, I'm here. So
Yeah.
feel free to turn on your mics and ask questions. I'll fill my water and then I'll come back in a minute. Yeah.
Yeah, sure. Nishad, we can start?
Yes. Yeah, sure. Okay. Yeah. Is it visible?
Yes, visible.
So yeah, welcome back everyone. If there are any questions or concerns, please ask them. Otherwise, we will apply this theory to prove Schoenberger's theorem. Okay, so let's go back to what we want to do. Our goal is to prove that in a two connected cubic graph, every edge belongs to some perfect matching. Okay. So, okay. So before that, let's look at one more quick thing. Let's go back to this corollary. This corollary tells you when does G minus U minus V not have a perfect matching? It does not have a perfect matching if and only if the original graph G has a barrier containing U and V. Okay, we will write another corollary of this and then we will go to Schoenberger's theorem. So let's write down one more corollary. I will erase these things. Okay, so now I want to understand one more thing and you will see why. So supposing I have a perfectly matchable graph. I have a perfectly matchable graph and I want to understand each edge of G belongs to some perfect matching if and only if something holds. Okay, and I will give you the hint. You can directly come from here. I want to write down a statement here. A perfectly matchable graph has the stronger property that every edge belongs to some perfect matching if and only if some statement over here about barriers. I'll write a bit more to give you a hint. Every barrier of G has some property.
Somebody has written something.
There is no barrier set. No, that's too strong actually. First of all, the empty set is the barrier by definition. Not a very interesting barrier. Another example is every single vertex is actually a barrier. If you delete a vertex, you will get exactly one odd component and possibly some number of even components. So every vertex is also a barrier. Yeah. Maybe you mean something slightly different, Sumanta. I'll give you another example where there is a non-trivial barrier. So here is a perfectly matchable graph. It is actually a two-connected cubic graph. Here is a two-connected cubic graph, and here is a barrier. You delete three vertices, and you get three odd components. So there is some property of the barrier I'm looking for. You can see some property of this set. You see some property? It has some nice property. Every barrier is an independent set. Exactly. Every barrier of G is an independent set. People in CS call it independent set. People in maths call it stable set. Yeah. Every barrier is a stable set. This is a property that you can infer directly from this corollary. Because what does it mean? If an edge does not belong to a perfect matching, let's look at the negation. If an edge does not belong to a perfect matching, any perfect matching, let's say the edge is UV, then you know that G minus U minus V has no perfect matching. That means there is a barrier containing U and V. That barrier has an edge joining the two vertices U and V. So it is not a stable set. Right? Okay. So we just proved one direction and the other direction is easy. Right? So both directions are immediate consequence of this corollary. So here we have another corollary. The point of this corollary is, if I have a graph that is perfectly matchable, and I want to prove that every edge belongs to some perfect matching, I will instead prove that every barrier is a stable set. If we prove every barrier is a stable set, we are done. Okay. So now let's go to Schoenberger's theorem. So it suffices, or it is equivalent to showing that every barrier is stable set or an independent set. Yeah. So we will prove this. Every barrier is stable. Okay, and actually the argument is almost the same as we did in Peterson's theorem. Okay, so let's consider a barrier. What is a barrier? I delete some number of vertices. Let's say I delete 5 vertices. And I get 5 odd components. Okay. There might be some even components. I will not draw the even components. Okay. I'll delete 5 vertices. This is the barrier. And I get 5 odd components. That is the definition of a barrier. Okay. And we just need to argue that there are no edges inside this. Can everybody see this argument? It's just counting again. Can you do some counting and see why there are no edges here? I claim that there are no edges with both ends in this set. If you see it, you can type in the chat box, yes. Exactly. Number of edges leaving B equals 15. This is equal to number of edges coming from the 5 components. Yes. We observed earlier that from each component, you will have at least 3 edges coming out. So at least 15 edges coming out of the components. They have to go into this set. And there are at most 15 edges coming out of here. And that will happen only if there are no edges inside the set. Therefore, 15 equal to 15. Therefore, there are no edges inside the set. If there is any edge inside the set, you will have very few edges coming out and too many edges going in. That is a contradiction. Right? So therefore, we have proved that every barrier is a stable set. And we use exactly the same ideas. Right? The only thing is, we exploited Tutt's theorem further to get something about when does an edge belong to a perfect matching. Right? Okay. So we are done. QED. Are there any questions or concerns? So we have proved Schoenberger's theorem from 1934. Okay, good. So now let's move on. So I want to tell you some important theory in matching covered graphs, right? So in the rest of the, I guess we have another 40 minutes. In the remaining 40 minutes, I will try to tell you some of the important concepts in the theory of perfect matchings. And maybe if there is some time, I will tell you some places where it is applied. And I will give you maybe links to some YouTube talks, which you can check out later, where that theory is applied. So you can also watch some more videos afterwards if you're interested. Okay. So, theory of matching covered graphs. Okay. And the point is that if you want to answer questions about perfect matchings, you don't need to worry about all graphs. You can just focus on matching covered graphs. So that is why there is a lot of theory on these graphs, right? I will list down some important topics that are part of this theory. One is barriers, which we have already talked about. Barriers are really important in the study of perfect matchings, as I hope I've convinced you in the last few minutes. Okay. So, are there some cool properties of barriers? Let me tell you a very cool property. Here is a theorem proved by Kortzig. I think it is 1964, if I'm not mistaken. Yeah. The maximal barriers of a matching covered graph partition its vertex set. Whenever you see the word partition, you are thinking that maybe there is an equivalence relation, right? Equivalence relation will give you equivalence classes. It will give you a partition. So, any guesses on what the equivalence relation is? There is an equivalence relation over here. Any guesses what that equivalence relation is? I'll give you a hint. Let's go back to our statement here. I want you to look at this and see if you can guess what is the equivalence relation. There is an equivalence relation hidden in this statement between the vertices of a graph. Two vertices are related if something happens. Can you guess what that relation is from this statement? Two vertices of a graph G are related if some property holds. Any idea? They are in the same barrier. Right. But there is something equivalent here. The equivalent thing is that G minus U minus V has no perfect matching. So that is what I was looking for. When it is equivalent to saying that they are in the same barrier. So the equivalence relation is U and V are related. Sorry. U and V are related if G minus U minus V is not perfectly matchable. This may seem a bit strange because maybe you want to see that the two vertices are related if this graph is perfectly matchable, but that is not correct. What you need is it is not perfectly matchable, right? Because then by the corollary, if this graph is not perfectly matchable, then it means that there is a barrier that contains these two vertices, right? And that will give you the maximal barriers. So if you look at this relation, you will get the maximal barriers of a matching covered graph. Okay. Let me ask you a quick question. This is K33. In K33, can anybody tell me what are the maximal barriers? This is a bipartite matching covered graph. Any idea what are the maximal barriers in this set, in this graph, K33? Yes, one part is one barrier. You mean the color classes. 0, 1, 2 is a barrier, maximal barrier, and 3, 4, 5 is another maximal barrier. In the case of bipartite matching covered graphs, you will get exactly the two color classes, the white vertices and the black vertices. Those are your maximal barriers. Let's go to another example, which is not bipartite. So in the case of non-bipartite graphs, this is probably more interesting. So in this graph, where what I've done is I've taken K33 and I've replaced each vertex in one color class by a triangle. Okay. What are the maximal barriers here? It may not be so easy to see. We already see one maximal barrier. This is, by the way, a maximal barrier in this graph. And I will tell you what the other maximal barriers are. You may have to check a little bit. The other maximal barriers are single vertices. So we have how many barriers? 1, 2, 3, 4, 5, 6. These are maximal barriers. 7, 8, 9, and 10. 9 of them are single vertices, and the 10th one is the top 3 vertices. These are the maximal barriers in this graph. The point is, they partition the vertex set. Right? And this is not trivial. This requires some effort. But if you are interested in the proof, you can try it yourself, or you can take a look at the textbook that I mentioned. Okay. There are some really nice proofs of this. So let's go back to Kotzig's theorem. Right? So this is called the canonical partition theorem. Or this partition of the vertex set. This partition is called the canonical partition of a matching covered graph. Okay. This is one important part of this theory. I want to tell you some more things about this theory. So next I want to tell you about a method to break a given matching covered graph into smaller matching covered graphs. Okay. That is extremely useful in proving results in matching covered graphs. Okay. So this is called the tight cut decomposition theory. It is due to many people, but the main person is Lowas. So let me tell you what a tight cut is. Maybe I'll give you an example first. Let's go back to our previous page. Maybe I'll just draw it again. I'll draw a simpler example. So here is I want you to look at this cut. Take a look at this cut. Maybe I'll use another color for some contrast. Okay, this is a cut. And I want to ask you, what happens if you take the intersection with any perfect matching in this graph? So what is a cut? The cut is these three edges that are leaving the triangle. What is the intersection of this cut with any perfect matching? Must be an odd number. Yes, that is correct. So therefore, there are two possibilities, either 1 or 3. And it is not 3, it is 1. Exactly. So observe that for every perfect matching, the intersection is exactly 1. Yeah. Turns out these cuts actually play a very important role in matching theory. Let me tell you a cool consequence of this definition. So what I can now do is I can take the two shores of the cut. So for a cut, the two sides, x and x bar, they are called the shores of the cut. Okay. So what I will do is I will shrink one shore to a single vertex. That will give me a smaller graph. Let's draw the smaller graph. Let me just make a copy of this. Okay, I've made 2 copies of this. Okay, I'll just draw it again, sorry. So here is, what I'm going to do is I'm going to shrink this triangle into a single vertex. Okay, and I will use a different color for that. This is one graph I get. And now what I will do is I will shrink the other shore into a single vertex. So I'll keep the triangle as it is, and I will shrink the rest of the graph into a single vertex. Okay. Observe that in this particular example, I get K33 and K4. Yeah. But more important is that they are both matching covered graphs. Both of these graphs, these are called the C contractions, where C is my cut. My cut is C. These are called the C contractions of the original graph G. And if the original graph is matching covered and you take a tight cut, such a cut is called a tight cut. Such a cut C is called a tight cut. And if you take a tight cut, then the two C contractions are also matching covered graphs. This is not difficult to prove. I will give it as a DIY, do it yourself exercise. Okay. Given any matching covered graph and a tight cut, which means every perfect matching intersects the cut in exactly one edge. If you take the two C contractions, the smaller graphs you get will also be matching covered. Observe that for every vertex, this is a tight cut by definition of perfect matching. So I am not going to consider these tight cuts, okay? I am going to put a condition. Each shore has at least 3 vertices. Each shore has at least 3 vertices. Clearly, it is an odd number because of this condition. So therefore, I'm going to say it has at least 3 vertices. And this is going to be my definition of tight cut. Okay. So it satisfies this condition and each show has at least 3 vertices. Because if there are at least 3 vertices, then the two graphs I get, they are smaller graphs than the original graph. Right? Whereas if my show has only 1 vertex, then I won't get smaller graphs. One graph will be equal to the original graph. Okay. So now what you can do is, if you have a matching covered graph that has a tight cut, you can get 2 smaller matching covered graphs. Yeah. And now if the smaller matching covered graphs have tight cuts, then again you can get smaller matching covered graphs. You can do this in a binary tree fashion, right? So your graph G, if it has a tight cut, you get 2 smaller matching covered graphs. If any of them has a tight cut, you again get 2 smaller matching covered graphs. You keep doing this procedure. At the end of the day, you will get a list of matching covered graphs that do not have any tight cuts. Yeah. For example, here, this is a small example. There is one tight cut. I get K33 and K4. And you can check that in these 2 graphs, there are no tight cuts. So therefore, you stop here. But in general, these graphs may have tight cuts and you get smaller graphs. Right? So in this way, you can take any matching covered graph and you can decompose it into smaller matching covered graphs. And the smaller graphs will not have any tight cuts. The question is, why is this interesting? Right? So one reason is because for a lot of problems in matching theory, you can actually, instead of looking at all matching covered graphs, you can just look at the smaller ones that don't have any tight cuts, answer the problem for that family, and then you get a corollary for all matching covered graphs. Okay? That's one reason why the tight cut decomposition is very important. I'll try to give you some example if there is time. Okay. Are there any questions, concerns? And another point is, whenever you see some decomposition like this of a graph into smaller graphs with stronger properties, a natural question arises, is this decomposition unique? For example, if I have a graph and let's say Sumanta has the same graph, right? And we both do the tight cut decomposition on this graph. I may choose some tight cuts. Sumanta may choose different tight cuts. We are not communicating. And then we meet to compare the list of graphs we get. Loas proved that this is unique. For any matching covered graph, no matter how you choose the tight cuts, the final list of matching covered graphs you will get will be the same. There is one small caveat. I will tell you that caveat in a moment. Okay. So is the overall discussion clear? So I'll just write down Loas' theorem. I need some terminology to tell you Loas' theorem. Maybe I'll go to new page. So matching covered graphs that do not have any tight cuts. They are called bricks if they are non-bipartite. And braces if they are bipartite. Okay, so these are definitions. What is a brick? It is a non-bipartite matching covered graph that does not have any tight cuts. What is a brace? It's a bipartite matching covered graph that does not have any tight cuts. Okay, and in matching theory, there is generally a very big distinction between bipartite and the general case. Bipartite problems are always significantly easier than the non-bipartite or the general case. Okay, this is something very particular or peculiar about matching theory, although you also see this in other areas of graph theory, but I would say it is particularly pronounced in matching theory. So that is the reason to distinguish between these two. And what are examples? In the previous example, on 8 vertices, we have this matching covered graph G. We have this tight cut, and what we get is 1 K4 and 1 K33. This is a brace, and this is a brick. So this procedure that I explained is called the tight cut decomposition procedure. I take a tight cut, I take the two contractions. Again, if there's a tight cut, I take the two contractions. Okay. So what will happen at the end of the tight cut decomposition procedure is you will get a list of bricks and braces, right? And Lovas's theorem says Lovas proved the following. Any two applications of the tight cut decomposition procedure to a matching covered graph yield or produce the same list of bricks and braces. Right? So when you do this procedure, you will get a list of bricks and braces. And what the theorem is saying is the list of graphs, the list of bricks and braces I get is the same as the list Sumanta will get. There is one caveat. I may get 4 copies of the Peterson graph. Sumanta will also get 4 copies of the Peterson graph, but his copies may have multiple edges. Okay, so or he may have one Peterson graph with two multiple edges. I may have a Peterson graph with 3 multiple edges. But the underlying simple graphs will be exactly the same. So to write this, we generally say up to multiplicities of edges. If you don't like multiple edges, you can just take the underlying simple graphs, and now the list will be exactly the same. If I have 4 copies of Peterson graph, Sumanta will have 4 copies of the Peterson graph. Right? Questions, concerns? So this is actually, I would say, perhaps the tight cut decomposition theory is one of the most important parts of matching theory. Let me give you one example. I won't have time to go into details of the example, so I will just try to give you some sort of motivation. So in structural graph theory, including perfect matchings, one of the things we really are interested in is characterizing certain graph classes. For example, most of you may have come across planar graphs. If you have come across planar graphs, you probably know Krutowski's theorem, which says that a graph is planar if and only if it does not contain K5 or K33 for a certain definition of contain. Okay? Either minors or topological minors. If you don't remember the word, don't worry, right? But basically it tells you that the only reason a graph is not planar is because it contains K5 or K33 in some sense. Okay? So this kind of result is, one could say, the holy grail of structural graph theory. This is the kind of result structural graph theories are really excited about. right? You want to characterize the whole class of graphs, a very rich class of graphs, using some forbidden subgraphs. Okay. So similarly, in matching theory, there is a class of graphs called, one of the most important open problems in matching theory is to characterize Tappian. I won't define this. I will just tell you some motivation for it. To characterize Tappian graphs. So this is related to counting the number of perfect matchings. So this was introduced by physicists in 1960s, mainly a person called Castellani. So they were interested in counting something in physics. I don't know. It turns out it is equivalent to counting the number of perfect matchings in certain planar graphs. Okay. So they realized that it was not too easy. They were not going to formalize it. Back then, people did not even have definitions of NP, co-NP, and P. This was early 1960s. What they did is they realized that if the graph has some property, if you can orient the edges, basically you get a directed graph from your undirected graph. And the directed graph has some property, which is called Pfaffian orientation. If your graph has a Pfaffian orientation, then what you can do is you can compute the determinant of a certain matrix. And from that, you can directly get the number of perfect matchings of the original graph. Okay, I will not go into details. If you're interested in details, you can go to my YouTube channel and there is a whole talk that is recorded. I gave a talk at Ahmedabad University a few months ago. So you can take a look at that. Okay. So the point is, if your graph has a Pfaffian orientation, then you can compute the Pfaffian orientation and the number of perfect matchings in polynomial time. Of course, back then, there was no concept of polytime. Okay, but they understood that you can compute the determinant of a certain matrix. Okay, so now the question is, what are the graphs that have a Pfaffian orientation? So the question is, can we characterize those graphs that have a Pfaffian orientation, whatever that means? Okay. So these graphs are called graphs that have a Pfaffian orientation. They are called Pfaffian graphs. Okay. And this is probably one of the most important open problems in matching theory. And it is well understood for bipartite graphs. However, for non-bipartite graphs, we don't really understand them. In particular, the problem is not known to be in polytime. Okay. So, but here is the cool thing. Because it is related to counting number of perfect matchings, you can restrict yourself to matching covered graphs. But now you can actually restrict yourself to bricks and braces. So if you can solve this problem for bricks and braces, then you can solve this problem for all matching covered graphs, and therefore for all graphs in the world. Okay, so this is the point I want to make. It suffices to solve for bricks and braces. And the way you prove this is you prove the following theorem. G is a matching covered graph. Take a tight cut. C is a tight cut. What you prove is the following. G is Pfaffian. whatever that means, don't worry about that. Think of this like planar, if you like, okay? Although it is not the same, of course. G is Pfaffian if and only if both C contractions of G are Pfaffian. And if you prove this, then it follows from Lois's theorem that a graph is Pfaffian if and only if each of its bricks and braces is Pfaffian. So this implies, or double implies rather, every brick and brace of G is Pfaffian. Okay? So if you prove that all the bricks and braces are Pfaffian, if you know that all the bricks and braces are Pfaffian, you know that the graph is Pfaffian. And if you know that the graph is Pfaffian, then all the bricks and braces are Pfaffian. Therefore, if you can characterize the Pfaffian bricks and braces, then you can characterize all Pfaffian graphs. Okay? And you can add matching covered here, although it doesn't really matter. You can also define Pfaffian for all graphs. And if you solve the problem for matching covered graphs, you can solve the problem for all graphs. Okay? So, and you might ask, can the bricks and braces be computed in polytime? The answer is yes. You can actually compute the bricks and braces of a matching covered graph in polytime. That requires the result of Edmonds, Loas, and Pouilly-Blanc from 1982, which I don't have the time to go into, so I might skip that. Right? So, using their result, you can actually compute bricks and braces in polytime. Right? So, this is one example of a problem, but there are many problems in matching theory where you don't need to look at all matching covered graphs. You just need to look at bricks and braces. And if you solve the problem for bricks and braces, you have a solution to all matching covered graphs. Okay? So that is the importance of this theory of the tight cut decompositions. Okay? I want to mention one more thing. So let's go back to the previous page. We talked about two things. One, we talked about the barriers. The next, we talked about the tight cut decomposition theory. Okay. Let's look at one example, by the way. This theorem that I told you. A matching covered graph is Pfaffian if and only if each of its bricks and braces are Pfaffian. So I'll tell you, in this graph, the bricks are K4, 1 K4, braces are K33. K33 is not Pfaffian. That needs a proof. Therefore, by the theorem, the graph is not Pfaffian. Okay, if you have one brick or brace that is not Pfaffian, then the whole graph is not Pfaffian. Okay, so this is another part of the theory. Maybe I'll erase some things and I will tell you more parts of the theory. And the point is, well, maybe I'll just write the gist here. Every matching covered graph admits a unique decomposition into bricks and braces. It is unique except for multiple edges. And in most problems, like Pfaffian orientations, multiple edges don't matter. We allow multiple edges because they actually make the theory work very nicely. Without multiple edges, the theory is not so nice. But when you actually look at problems, multiple edges don't really matter in most problems. Right? And the other point is that most problems, like Pfaffian orientations, reduce to bricks and braces. By reduce, I mean, if you solve the problem for bricks and braces, you have solved it for all graphs. So now let me tell you another part of this theory. Most of you may have seen two connected graphs, right? any basic course in graph theory will tell you about two connected graphs, right? If you have seen two connected graphs, you may have seen an ear decomposition theorem of two connected graphs. This was proved by Whitney in 1932. Every two connected graph admits an ear decomposition. What is an ear decomposition? Let me give you a quick example. Here is a two connected graph. What you can do is you can start with some cycle and you can keep adding paths. Here is one path. Maybe I'll use another color. I have added one path. Then I will add another path. Then I will add another path. And now I will add one more path. At every step, I am adding one path to the graph. This path is completely disjoint from the current subgraph, except for the two ends. The ends are going to be in the subgraph, but all the new vertices and edges, they are new. They are not in the existing subgraph, right? So basically what you have is some subgraph and you're adding a path like this. Okay. This is called an ear decomposition. And you can think of it as an induction tool for two connected graphs. If you want to prove anything for two connected graphs, one of the first things you should try is the ear decomposition theorem, which tells you that all two connected graphs can be generated like this. Okay. Similarly, there is a beautiful ear decomposition theory for matching covered graphs. For bipartite graphs, this was developed by Kotzig. No, sorry, not Kotzig. This was Hetier. Hetier in 1950s or 60s, I don't remember. And in the case of, this is only bipartite. But in the case of non-bipartite matching covered graphs, you need some more fancy things. This was developed by Lowas and Plummer. 1980s. Okay, and this is another beautiful part of this theory, which is extremely useful in solving problems. And it interacts very nicely with the tight cut decomposition theory. So there is a constant interaction between these two theories. If you stick to one, you may not be able to solve your problem. If you want to solve the problem, you need to understand both of these and kind of understand how they work with each other. Okay. So that is the ear decomposition theory. Essentially tells you that every matching covered graph, you can build it from a cycle. You can take a cycle on even number of vertices and you can keep adding ears, which means paths, to construct the whole graph. So that every graph in the sequence, every subgraph in the sequence is also matching covered. Let me give you one quick example of a non-bipartite graph. I'll take my example that we started the talk from. We started the talk from this graph. Yeah. So let's see how to do an ear decomposition. So first I will take a cycle. You can't choose an arbitrary cycle, but anyways, I won't go into that. I'm going to choose this cycle. Now what I will do is, this is a matching covered graph. This is an even cycle. Every edge belongs to perfect matching. Now what I will do is, I will add an ear. Path of odd length. Odd length because odd by length I mean number of edges. Okay? Because the number of vertices has to be even. So you can't add paths of even length. You have to add paths of odd length. So that the number of vertices is an even number. But observe that I'm not going to add any path. I'm going to add a path that gives me a matching covered graph. This is a matching covered graph. And observe that this is also bipartite. Now if I want to get this graph, you might say, add this edge. There is a problem. this edge is not in any perfect matching in this graph. To get from here to here, you have to add two edges simultaneously. In general, you have to allow for the addition of two vertex disjoint ears simultaneously. And this is what Loas and Plummer proved, that you can always add either one ear called a single ear, or you can add two vertex disjoint ears simultaneously. This is called a double ear. So that every graph in the sequence is matching covered. If you want only bipartite graphs, you don't need double ear, which is why this theory is easier. Bipartite matching covered graphs, ear decomposition theory. But the non-bipartite ear decomposition theory requires the addition of double ears, which is why this theory is more difficult to prove and also to use. Okay. And there is one part I want to mention. So this ear decomposition theory is closely related to another part called dependence relation. Dependence relation is a relation on the edges of a matching covered graph. And instead of proving these results directly, what you can do is you can first understand this theory, and then you can apply this theory to prove ear decomposition results as immediate corollaries. And this dependence relation was introduced by Carvalho-Lucchesi-Murthy in 1996. And there are whole chapters dedicated to this theory in their book. Right, so I will just stop here. These are some parts of the theory I want to tell you. Right, so the barriers theory, the canonical partition theorem, the tight cut decomposition theory, using which you can reduce problems to bricks and braces. But this is not enough. You still need to solve the problem for bricks and braces. This is where ear decomposition theory becomes very helpful, and they actually play with each other in a nice way. So you need to develop more tools. And the ear decomposition theory, to understand that, one can also understand the dependence theory that was introduced by Carvalho-Lucchesi-Murthy, and that is recently used by one of my students to prove a lot of cool things. So what I will do is I will share some talks with all of you through Dina. And now after this talk, you should be able to understand and follow those talks, where you will see some of these theories being explained and applied. But I don't have time to cover that in this talk. So I will stop here. Thank you.
Thank you, Nishad. And any questions? Any questions from the participants?
Yeah, feel free to ask anything. From the list of bricks and braces and the multiple edges, one can go back to the original graph. Yeah, I will just quickly address that point. So what we discussed is this, we discussed this contraction business, right? So what you do is you take a cut. This is X bar, and you take the two contractions. This is little x bar. So I shrink this entire set into single vertex, and then I shrink this entire set into single vertex. And I get the smaller graphs, G1 and G2. The point is, if I want to go back from here to there, I need to choose a specific permutation of the edges. So this operation is called splicing. This is the reverse. What you can do is you can take two graphs, G1 and G2, and two vertices x bar and x, so that the degree of x bar is equal to the degree of x. Degree of x bar in G1 is equal to degree of x in G2. And now what you can do is think of erasing these vertices. When you erase these vertices, you will have some edges like this. I'm not erasing the edges. Now I can join these edges, but I have some choice. For example, I can do this. Or I can choose a different permutation. I can consider, I can consider a different permutation of the edges. I can make this one go here and make this one go here. So when you go to the reverse, there is some choice. But if you know the permutations that you used, then you can go back to the original graph. I'll give you one concrete example. This operation is called splicing. Right? So you take two small graphs with this property, degree of x bar is equal to degree of x, and then you construct a bigger graph like this. So what you can do is, you can take the Peterson graph, observe that Peterson graph is obtained by splicing two wheels. What is a wheel? Wheel is this graph. This is called W5. If I shrink this into single vertex, I will get this graph. If I shrink the outside to single vertex, I will also get this graph. So Peterson graph is obtained by splicing two W5s, wheels on 6 vertices, sorry. The notation is W5, number of vertices is 6. So if I splice two wheels at their hubs, I can get the Peterson graph. But depending on the permutation I choose, I can also get the pentagonal prism, which is a planar graph. It is different from the Peterson graph. Peterson is non-planar. So both of these graphs, Peterson and pentagonal prism, are obtained from splicing two wheels. The cut I chose here is not a tight cut, but you can make such examples even for tight cuts. Okay. So to go backwards, you need to know what permutations you used. You need to apply the correct permutation in the splicing. Yeah, does that answer your question, Suchi? Thanks.
Any other question?
Thank you.
I have one thing like
Yes.
whether these kind of theory are used in other kinds of matching, like variants of matching.
What is the other matching you mentioned?
Means variants of matching, like induced or something. People do characterize or yet to know.
Yes, I believe people have used some of this theory. I am not too familiar with induced matchings. Recently, a student of mine looked at this kind of matching. There is a reason for looking at it. I won't go into the reason. So this is called a V matching. What is a V matching? V is a vertex. So V matching means the vertex V, this is particularly studied in cubic graphs. In cubic graphs, you want a V matching. What is a V matching? V will have degree 3. Every other vertex will have degree 1. So it is a spanning subgraph where a particular vertex has degree 3, which is an odd number, and every other vertex has degree 1. This is called a V matching. Right? Let's look at one quick example. Here is the graph K4. K4 has a V matching for any vertex you choose, clearly. So recently we studied V matchings. There's some context which I'm skipping. And there also, the theory of bricks and braces turns out to be very important. So this Santosh, my student, he was able to get lower bounds on the number of V matchings in two connected cubic graphs. And in these lower bounds, there are some parameters that appear, and they are coming from the tight cut decomposition theory. For example, the number of V matchings is at least, this is what he proved. Lambda is at least beta. What is lambda? Lambda is the number of V matchings. And what is beta? You take all the bricks and you sum up the number of their vertices. For example, if one brick has 4 vertices, another brick of the graph has 6 vertices. Then my beta is 4 plus 6 equal to 10. So this is the sum of orders of bricks of the graph G. And this is the number of V matchings in G. And he proved this result for all two connected cubic graphs. Right? So this is an example of a different type of matching where you can use this theory and this is tight. He actually gives a complete characterization of all the graphs that satisfy this with equality and its infinite family that is defined recursively. So I would assume that even for other kinds of matchings, like induced matchings and all, there may be potential to use this theory, but I am not too familiar with the literature.
Okay, fine. Okay, thank you.
Thank you.
Any other question?
Any other questions?
Okay, if there is no more question, let us thank Nishad. So it was really a very interesting lecture.
Thank you very much. Yeah, I'll send some links to you. If you could share it with the participants, that would really.
Sure. So there is a small announcement,